Can you hear me? Hello?
Yes.
Can you hear me?
Yes, sir.
Yes, sir.
Can you hear me? Hello? Hello?
Yes, sir. Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Yes, sir. We can hear you.
Okay, let me start. Actually, problem is I think with the IIT system. Around 12 o'clock, I think too many people try to log into MS Team. So if I do it 10 minutes before it, I get quickly connection. But if I do it at the nick of the time, then it takes time. Okay, so that I just want to have the topology basics in that you should understand that this non-empty set and tau is a non-empty family of subsets of X. That means it's a subset of power set of X. That means tau is a family of, did not be all, some subsets of X which satisfying, look here, satisfying 1 X phi belongs to tau. 2 if y I belongs to y, arbitrary I is an arbitrary index, is here subset of tau, then union of y I belongs to I belongs to again tau. That means the arbitrary union of members of tau is again in tau. And third is this. Whether you take 2 or n, it doesn't matter. If finite basically, u1, u2, un is a subset of tau, then intersection. This is finite, belongs to tau. Okay, I'm just recalling in that. So you have these three conditions satisfied. Okay, if they do not satisfy, if it doesn't, tau doesn't satisfy, then forget about it. Don't work with that. Okay, then tau is called a topology. Topology on X. Okay, and X tau, this pair is called a topological space. It's called a topological space. Often I will use this top for abbreviation of topological. Topology or topology. Okay, so topological space. So we're starting with X tau topological space. There is the smallest topology. Remember that. The smallest topology is the trivial or indiscrete topology. in discrete, opposite to discrete topology. Smallest topology on X, and the largest topology on X is the discrete topology. Here tau equal to just these two, X and phi. And here tau equal to the whole power set of X. Okay, right? So this is the topology. Definition is very simple. Okay, then we got this thing that, so if you start with the metric space D, this is the way we generate open set, that gives you a topology, tau D. So that though we write XD to indicate same as this, but actually topological space, corresponding topological space will be this, X tau D. But usually we indicate, you use this XD to indicate the corresponding topological space also. So this is a metric topology, actually it's called metric topology. So conversely, suppose you have a topological space, and if there exists, if need not be, because we have shown that this can never be, if X has more than one point, it can never come from a metric. If there exists a metric D such that tau is, this tau is means the notation, topology generated by D is same as tau, then X tau is called metrizable. And tau is called the metrizable topology. Metrizable topology means topology is coming from a metric. Like if you have X as more than one point, okay, then this is not metrizable, whereas this is always metrizable because it comes from a discrete metric. And if it comes from a complete metric space, suppose if there exists a complete metric, if you take complete metric, then it's called completely metrizable. Completely metrizable. Okay. And then this is called a complete metrizable topology. It's a completely metrizable topology. Then that will be called a, here you should have one more thing, completely metrizable topology. Okay, right? And then I told you that how to generalize this concept, because this is a neighborhood of X in a metric space. That means you have distance metric, but in general topological space you do not have the concept. Then we'll take any open set U. U is open, same as U belongs to tau. Okay, U belongs to tau is same as to say U is open in X tau. Sometimes we say tau open because when if you incidental, if you consider more than one topology on X, then it should be clear that you are taking open set with respect to which topology. Okay, then here given X belongs to X, if X belongs to U open, then we say that U is a neighborhood of X. Of course, this is understood, but if you need to be specific, you can write it. So this is the thing. With this, that I gave you the motivation that how it works. But that means when you go to the metric space, it will be the same thing what you got in the metric space. Now, theorem 3.2 already I told you that But what is closed set now? If you have a subset of X, as before, A is called closed or tau closed. It's called closed in X tau or tau closed if X minus A is open. That means if X minus A belongs to tau, that is X minus A is open in X tau. Okay. Now we have defined that you should read that here with the X tau topological space, X belongs to X, U is an open set. Then we have defined, we could define interior point, A is a subset of X. We could define interior point of A, closure point of A. Instead of ball, you'll have to replace it by an open set containing that point X. Closure point of A, accumulation point of A, okay, and boundary point of A. Whatever definition you got in metric space, same definition will work. Only thing, if you have X, you are calling interior point of A or closure point of A, accumulation point of A. Then instead of BXR, a ball, you'll have to take an open set containing U. Then U is called a neighborhood here. Same thing you will get here. Okay. And then theorem 3.2, I have given you the exercise. Same results will follow. Okay. And make sure that I say T1 space. If every singleton is closed, if it's called if X is closed in X tau for all X belongs to X. So I already told you that if it contains more than one point and tau is trivial, then it is not a T1 topology. Okay. In fact, we do not usually consider this. We need minimum T1 topology. In fact, we need more. Basically, if you want to study further, we need our topological spaces to be a little bit nice. So I am coming to this. Here I am defining, I don't know whether I have defined here somewhere, it must be defined. Let me tell you that. It is Hausdorff topology. His name is Felix Hausdorff. In mathematics, often you'll hear his name. Actually, people started doing topology before him also, but they didn't call topology or they didn't know what he was doing. Like Fréchet started metric space, but actually axiomatic foundation, axiomatic formalization, like that. Formalization of topology was done by Hausdorff. In the year 1913, 1914. Okay. So in his honor, there is a space called Hausdorff space, that Hausdorff topology, Hausdorff space. What is that? Hausdorff space, or we call it T1, so it's called T2 space. What is this? Look, in a metric space, if you have 2 points, x not equal to y, xy in x, then if you take r less than dxy, since x not equal to y, dxy is positive, then you can see easily check that pxr intersection byr. So I'm not very sure, you can take r by 2. I think r will work. I'm not very sure. Let me equal to 5. Because if z belongs there, I think you need r by 2. If it belongs here, then you see that dxz, so dxy, need that, is dxz plus dzy, triangle equality. But this is here, so this is r by 2 less than r by 2, this is less than r by 2. So this is less than r. But I have taken, so I could take this. 2, I don't need it. Okay, fine. I was just wondering. I think this will be all right. So basically, the idea is, let me tell you that. What is the idea? Okay, so, oh, it is coming to r. Sorry, r plus r. So r by 2 होना चाहिए. ठीक है. This is fine, but this is fine. This is fine. So here you take r by 2. Here you take r by 2. This you take, here it is fine. But here you take the ball r by 2. So this you are getting contradiction because you have chosen r less than dxy. Here you are getting dxy less. So you get a ball. Basically, the idea is that if you have ax point y, so dxy is r. So you are taking, this is r by 2. So if you take a ball, that will be here, and that will be here. But this is open ball, though they are touching, it won't intersect. Okay, so this is the idea that you are doing. So that means what you are getting, that any 2 points, distinct points in a metric space, can be separated by 2 disjoint neighborhood. Disjoint neighborhood. Look, this is a neighborhood of x, this is a neighborhood of y, and there they are disjoint. Same thing it happens in the topological space. Now the neighborhood, it will be an open set containing x, open set containing y, such that there exists. That means formal definition will be this. A topological space, this definition. A topological space x tau is called Hausdorff if given any pair of distinct points. Here I am being emphasizing distinct points x and y. In x there exist open sets u and v in x tau such that u is a neighborhood of x, such that so that x belongs to u, v is a neighborhood of y belongs to v. There exists the pair, and intersection v is empty, disjoint. So the balls there have replaced by this. If you have it, it's called it Hausdorff. Now look, again x tau, if you take trivial topology, if it has got more than 1 point, okay, it is not Hausdorff. In fact, It's called Hausdorff or T2 if. Okay, so you can check that, proof that. First proof that, check. A T2 space. T2 space means a T2 topological space. A T2 space is a T1 space. Check. Okay, that means any Hausdorff space, in a Hausdorff space, every singleton is closed. That you can prove that. You should prove it. Okay. You just use the definition of closure point. Okay, and the neighborhood you will get that. Now look, so see, this is not even T1. If it contains more than 1 point, so it can't be T2. On the other hand, if you have discrete topology, if it is discrete, then X tau is Hausdorff. As you proceed further, you need to put some restrictions on topological spaces because we can't work with a pathological topological space. Okay, see, then X tau is Hausdorff. Now look here, another good example that I discussed yesterday. Look, if you have X tau, tau is cofinite topology. Remember, cofinite topology means tau, it is X, phi, and those sets, subset of X such that X minus U is finite, complement is finite. Okay, so closed sets are precisely closed sets. X, phi, and all finite subsets of X. Okay, right. So obviously it's a T1 space, but now if X is finite, that I said if X is finite, then actually cofinite topology will be discrete. So that's why I told you that when we take cofinite topology, we take X infinite. So if you take X infinite, then it is not a discrete topology. Okay. Now look, if X is finite, it is discrete topology, so it is Hausdorff. But if it is infinite, okay, then I am saying, in fact, I can prove more things, that if U and V are non-empty open sets, in this case are non-empty open sets, then U and V must intersect. U and V. So if you don't get to non-empty sets which are not disjoint, then how it can be Hausdorff? So you can prove it. Look how it can prove. Look, X minus, look what you can do. U intersection V, sorry. By De Morgan's law, we'll have X minus U union X minus V. Okay. Now look, by the definition of open sets here, okay, it has to be finite. Look, I am taking non-empty, so U is not phi, so it can't become X. Okay, so U has to be non-empty, so U has to be either this or this. Even if it is equal to X, it will be empty set, finite. Similarly, this is finite. Look, listen to the argument. So you are getting union of two finite sets. So on the right side, you are getting a finite set. Whereas if U intersection V is empty, if you assume empty, then you will get equal to X. But X I have assumed infinite. Here you get infinite, left hand side, right hand side you are getting finite. You are getting a contradiction. So that you will always have it. So if you two non-empty subsets or say non-empty open sets always intersect, then it cannot be Hausdorff. So that what I have got, I have got this x tau, x is infinite, tau is cofinite topology, is not Hausdorff. On the other hand, I got the idea from the metric space. Okay, so any metric space is Hausdorff. In fact, metric space has stronger properties. As we proceed further, I will explain that. This is Hausdorff. Okay, fine. So you got this. So, in fact, I have used it. Result in page 133. I must have defined Hausdorff before. Let me see where definition. .10, page 132 that I have defined. This is very important. In topology, often you will hear his name. Like in major theory, often you will hear this fellow's name, Liebig and Bodel, two Bodel. There are two Bodels in history, but this is Bodel, one Bodel, major theory. Okay. So Liebig and Bodel, that in major theory you will hear. Here in topology, Hausdorff will often hear. And when you do function analysis, often you will hear Banach. Okay. So you can't help it. You will hear many names often. Okay. Now, look. I'm coming to this point. Now look, page 130, go back. So Hausdorff I have defined. I will come back to Hausdorff later on. Should I go back? Okay, I will come back to Hausdorff. But here, since page 130, I have defined already dense set already I have defined. No add dense. After topology, I will teach you Baird's category theorem. I have already uploaded it. This is next note. This is note number 617, I think. Note 17. Baird's category theorem. This is a small note actually. Note number 17. This I will start on Monday. Okay. So here, these things are very important in this. Dense, you know, already I have done that. If A bar equal to X, then A is called dense in X. Whereas A is called no hat dense. A is called no hat dense, means if you have the interior of A bar is empty. Basically, no hat dense. Later on, I will see something more general. But this is very almost an empty set actually. It's a thin set. Thin. Okay, thin set. Okay, so interior of A bar is this. Okay, right. This is not something like, look, if I take in a metric space, you see that. If I take any point, okay, it's closer to itself. Okay. Suppose it's non-discrete. If you take like this, if you take this first. So you have this, the interior of this, because this is X in here. It doesn't contain an interval, so this is 5. So any singleton in R is no add dense. Okay. You can have better example. Cantor set on that. That I will talk later on. Okay, right? So this is dense set. It is opposite, nowhere dense. That taking the interior of A bar is empty. Now look here, like there can be a big change between interior of A an interior of a bar. Like example I am giving you in R here. I think I have given a problem in minor exam that is related to this basically. I just asked, is it true or not? Look, if you take in this, if you take A equal to Q, then int of Q is empty. But whereas int of Q bar, that is R, you are doing in this topological space, metric space, that is R. So don't forget about the definition. This makes a big difference. I'm taking even this closer so that Q is, look, Q is not nowhere dense. Q is not nowhere dense. Okay, be careful about it. Now look, but though Q is not nowhere dense, now look, I can write Q equal to union Q, Q belongs to Q. But look, Q is countable, that is countable infinite. That means it is countable union, but each point already I have seen that each Q is nowhere dense. While looking for the size of the sets, even countable sets, they are also considered small sets. This is nowhere dense. So you are getting Q. Look, Q is not nowhere dense, but Q is a countable union of nowhere dense sets. But that means when in a topological space you have a set is a countable union of nowhere dense set, then it is called mega set. It has got many names: mega set, rare set. That inside it is basically empty, or set of first category. Usually set of first category, that is more prevalent term. Set of first category. Okay. That is called a mega set or set of first if there exists a sequence n of nowhere dense set such that A equal to this. That means you are having this. Let me define formally. So you have X tau, the topological space, A subset of X. Then A is called, suppose A can be written as this, countable union, N belongs to N is a natural number such that where each N is nowhere dense. Nowhere dense. That is int 2, 5. Okay, right. So if you have this, then A is called a mega set. Rare set I have not used it here. Some people use it, but this is more. These two terms are more well known. Mega set or the set of first category. Okay, right? That means Q is a set of first category in this. समझ गया? Q is a set of first category in this. Second category, if it is not first category, then it is called second category. This is very simple thing. But D, I put a star mark. If A is not a Meager set, that is not a set of first category, then it's called a non-Meager set, or okay, or a set of second category. If it is not first category, then second category. Then point is that the first category, second category is very important. If it is not a set of first category, then it is called second category. Why it is important? Okay. Reason is, later on we will do in the on Monday Bayes category theorem. From here it comes Bayes category theorem. Actually, Bayes category theorem, the known corollary, Bayes category theorem says something more, but one corollary is that if Xt is a complete metric space, complete metric space. Xt, it is a complete metric space. Then look, then of course you are having the topological space X tau D. Okay. Then X is of second category in X itself. This means topological space. This is a big theorem. If I had a theorem like this, I wouldn't have worked in my whole life. I would have been remembered for centuries. Okay, this is a big theorem. If Xd is a complete metric space, then X is of second category itself. Well, you may not have an idea why it is important. Reason is, look, if X is of second category in itself, that means what? Whenever you have this, something, suppose you get this, some Xn. And I know this is of second category in Xt. That means at least there exists n naught. Suppose I have such that interior of Xn naught bar won't be equal to phi. Got it? If it is second category, because if I have for each interior in the closure, if it is empty, then it will be X will be a set of first category. Now the thing is that after that not equal to phi, then you get a point here. And the reason is just existence of this point gives us many results, like function analysis particularly, but though in real analysis also true, that all the big theorems, the principle of uniform boundedness, open map theorem, closed graph theorem, except Hahn-Banach, these three, they depend on this. That is, but in the proof actually we need this. Okay, that's why it is important. In fact, in real analysis, I will also show that why it is important. Okay, I will give examples of that. Okay, right. In fact, I think you can prove this definition that second category. Suppose you assume that, say, I know this is a complete metric space, Okay. So R is of second category in this. Well, now there is a problem I have given. Show P, set of irrationals. Can't be written as a countable union of closed sets in this. It's apparently a small exercise on that. By if you use this, it is immediate. That I'm going to prove. Okay. But it has got big applications. Well, suppose it can be written. Suppose if possible. Listen to me. I'm giving you the proof. Suppose if possible, write P if possible. Write. If possible, assume P equal to union of Fn and where each Fn is closed in R. ठीक है? Now you see that P equal to what you got. So R, you get Q union P. So Q I can write this way. Union ठीक है? Now look, this is countable because Q is countable set. Here it is a countable family. So this is countable altogether. That means R is a countable union of here each singleton is closed. Okay, right? Are you getting? Okay. But by Baird's category theorem, it is of second category. Okay. But then there must exist. Look, here I know each of them is Noether dense. Okay, so there must exist a set here. One of them which is not Noether dense is not Noether dense, but each of them is here Noether dense. That means here there must exist. Okay, an N naught. So there exists N naught such that Fn naught is not Noether dense. ठीक है? But that means interior of Fn naught is non-empty. But look, Fn naught is closed. So this is same as this, not equal to. Now look, why it will give a contradiction? Because if you take X belongs to interior of Fn, it means what? An R, open sets are open intervals. So there exists delta greater than 0 such that interior point X minus delta to X plus delta will be contained in Fn naught. Okay. But look, Fn naught was a part of irrationals. Fn naught was subset of this. Because P was the union of all these. But here you are getting rationals as well as irrationals. And Fn naught is containing some rationals. But it contradicts this. So that it can't be written as a countable union of closed sets. Okay, got it? Okay, so this is the importance of first I'm showing the importance. And irrationals cannot be written as a countable union of closed sets. Okay. Later on I'll prove that suppose you take a function from this to this. Any function you take, consider. But the funny thing, here you have two sets. A, where X belongs to R, such that F is continuous at X. Actually, better you write C. So she will say it is continuous. Okay. And D you write X belongs to R. F is discontinuous at X. Then R equal to obviously C union D. And C intersection D is empty. Fine. But here I would try. Here C and D must have some property. It's not arbitrarily I say, you can say I will make these points at these points are discontinuous. I will choose a function and at this point I will make f continuous. You don't have a choice there. Whatever you try, C and D must satisfy certain property. Okay, so that's why you will have the restriction of your function, at which point you can choose it to be continuous, at which point you can choose to be discontinuous. Okay, like you think of that, you did undergraduate analysis, you think of that, first you take C equal to Q and D equal to P. That means try to find a function which is continuous at rationals and which is discontinuous at each irrational point. And next time you do this, second case, you do this. That means at each irrational, you get function is continuous, and each rational it is discontinuous. You see, out of these two scenarios, I am not going to tell you, you should figure out. One of them you will get, one of them you will never get. One of them you will never get, one of them you will get. Okay. So this is the application of that result. I proved that irrationals cannot be written as a union of countable union of closed sets. Okay. Right. So this is you should think of that. I will talk again about this. Now, exercise I have given that page 131, right? Well, one thing I have not done that. Okay, so everything I talked about, I'll talk about continuous functions and that in general topological space, that I will do that. But first, think about simpler things, convergence. Suppose here again, suppose you have sequence in X and X belongs to X. How will I define that Xn goes to X in X term? Look, this is very simple to define that. There in metric space I was taking that any neighborhood of Vxr will contain a tail of the sequence. That eventually members of the sequence will be here. But here the neighborhood is being replaced by an open set U such that X contains C. That means any neighborhood of X like U must contain a tail of the sequence. That means after a while everybody will be there. So that means, look, that neighborhood will depend on, okay, that eventually that A naught will depend on this. That I'm saying, look, the definition that Xn goes to X if and only if it is that result I have given for metric space. And now I have, oh sorry, definition 3.9, let xd, not xd, x tau. Definition 3.9, it will be x tau. Let x tau be a topological space and Xn be a sequence and X, okay, x tau. Definition 3.9. I told you that every ball neighborhood of X in a metric space you'll have to substitute by this, so that here there are or epsilon that was given this a neighborhood. Okay, so I am taking a neighborhood here. So that means I will say Xn goes to X if for any neighborhood U of X, any neighborhood U of X means this and U open. There exists a natural number, so that natural number will depend on U. Look, their natural number depend on this R or epsilon, whatever you need to do. But that means it dependent on this neighborhood. So here I am writing this belongs to N such that Xn belongs to X for all N greater than equal to Nu. Sorry, Nu. That should be the definition. This Nu will depend on this. That was this there also. Okay, right. Now the thing is that I am giving some giving the remark on that in metric space why it is called, it is nice because many of the properties you got nice sequential characterizations. particularly continuity and closure point. But here you will see that in reality this is not possible. But before that, convergence of sequence, suppose I take tau, and tau is a trivial topology. Okay, and take a sequence xn. Okay, and take any point. Will it converge to this? Look, I have taken any sequence, any point. And now my question is that this. Look, this is true because only neighborhood of x, because here you have only two sets in topology, x and phi. But if x belongs to is a neighborhood, then it has to be x, because phi doesn't contain any point. But once that means only neighborhood of x is here is x, and obviously everything you are working inside x, so that will x will contain all the members of the sequence. It goes. That means what you are getting. That's why it's not a. We start with officially, but it's not a good thing. That means here you are getting what? Every sequence converges to every point. Here you are getting every sequence converges to every point. Obviously, we will say that this is not a nice space. Okay. Yes, it's not a nice space. Okay. But it's a good friend because it often serves as a good counterexample. Now, if you take this, on the other hand, if you take this thing, discrete, that you already know that if you have discrete topology. Okay. Then which sequence will converge? Look, if it converges to x like that, what you did in metric space, then x is itself open. Okay. So it will contain, for this is the neighborhood of x itself, this is open. So u equal to take you this. So this will contain a tail of the sequence. That means xn belongs to this. There exists n u. U is that belongs to n such that but here it belongs to means what? Xn equal to x for all n greater than equal to this. That means xn is eventually constant. After a while, it has to be all x. Okay, though it is better than the previous one, still it's not a good thing on that. So we should have a, that means what it is saying. That means when you are going to study topology and that, because topology gives you the other areas of math, so that when I have a topology, it should have sort of, that's the big word, sort of good size. That means it should not be too small, too large. It should not be too small, too large. Too large like the discrete I have seen that, and also for trivial topology I have seen the case. So it should not be, it is an example that a topology should be a good topology in the sense it should not be too small or too large, because if it happens it's too small, then it will give you like the trivial topology many apparent nonsense, and that is you think not they are not good things. On the other hand, it will make you everything nice. But while studying a space and that, look, two situations you should avoid, that like everything is bad and everything is good. Okay, then you have nothing to study. Okay, right? So basically, you'll have to see that where something is good, something is bad. Something is good, something is bad. Okay, like when I have a continuous functions on a metric space and that, I will expect to, of course, constant function should be continuous, nice function should be continuous, not the bad function should be continuous, right? Same way, that depends on the topology also. We'll see that here if you take discrete topology, then any real valued function on it will be continuous. Okay, and here only the constant functions will be continuous. so that it should not be too big, too large. Okay. Now, thing is, what about this, that? Now, I am asking this question. I'm leaving it to this question to you. Look, I have got x tau, tau discrete, and I have got every convergent sequence. Here, every convergent sequence in x tau is eventually constant. Okay, there's you got. Now suppose you have this. Suppose you have a topology. Now the converse, and you have this thing, hypothesis. Every convergent sequence in x tau is eventually constant. Is it discrete topology? That's the converse. Now look, I'm going for a break. I'm giving you a break of 10 minutes. Now think about, if you want, I'm giving you this. If x tau, remember, if it is cofinite topology, if x is infinite, then it is not discrete topology. But what happens? That if x is infinite, of course you assume, because if x is finite, then tau cofinite will be discrete. You know that. X is infinite, tau cofinite. So what are convergent sequences here? Think about this. I will come back after 10 minutes. Okay? I'll think about it. Hello, ball. একটা প্রপার্টি ছিল, কি প্রপার্টি ছিল বলতে চাচ্ছি, জমি। এক মিনিট হোল্ড কর, আমি একটু পড়াচ্ছি, একটু ব্রেক নিচ্ছি, আমি বাইরে আসছি, কথা বলছিলাম নিচ্ছি। আর কি বলবি, প্রশান্ত মালাকা। হ্যাঁ সেকেন্ড নামে রাত হয়ে যাবে 8টা বেজে যাবে তো দাদা এসেছিল দাদা বললো না তার সাথে আমার খুব ফোনে কথা হলো দাদা বললো না কোথায় আজ করলো না যাওয়ার চান্স নেই হ্যাঁ আচ্ছা ঠিক আছে ভালো থাকিস রাখছি Hello, I want to start. Fine? Hello.
Yes, sir.
Okay, so let me show that what are convergence sequences here in cofinite topology. Okay, so you have x tau cofinite topology and x infinite. Suppose here xn goes to x. Okay, right? Got it? And take this set A, xn, those xn such that xn not equal to x. Okay, we are choosing those actions which are different from x. If possible, now look x minus a. Okay, look, first of all, its complement is x minus a. A is countable, so that this is open in cofinite topology. Its complement is a countable set. Also, look, A does not contain x because A only those xn's which are not equal to x, so that x belongs to x minus this. Okay, that means we are getting a neighborhood of x this. So if you have this, it should contain a tail of the sequence. That means so there exists n naught belongs to n such that xn belongs to x minus a for all n greater than equal to n naught. Look, that means what you are getting here. After a while, after n naught, everybody is here. Okay, that means outside, that means a, what is your choice about a? Xn not equal to x. Okay, xn doesn't belong to, particularly doesn't belong to a for all n greater than equal to n naught. Right, that means a has to be finite, right? Got it? You're done. A is finite. That means if you have a convergent sequence, it has to be eventually constant. Because xn doesn't belong to A implies xn equal to x. It is eventually constant. So you are getting every convergent sequence is eventually constant. But already I told you, if it is infinite cofinite topology, it is not discrete topology. Okay, not discrete topology. So here you get, make sure that you understand it. Okay. This semester you may not need it, but next semester you'll need it. So that now here, look. Now again, look. I'm saying sequential characterization of closure point, whether it is possible here. This is infinite. This is cofinite. Okay. Well, you take. I have a reason that you could do that. Take uncountable. Okay. Well, so that now look, take x belongs to x. I could do it infinite. I have taken for safety that. But what about this? Look, its complement, if you take u equal to this, its complement is a finite set, so u is open. Okay, right? Look, is U closed? No. Why? That's a technical. Look, remember cofinite technique I could take infinite. Closed sets are what? Closed sets to take just infinite. I don't think you need that. Just infinite will do it. The closed sets are what? X, phi, and finite sets, subsets of x. Got it? I'm just working out these examples to give you a feeling of the topology, general topology. Okay. Now look, this is not whole X. This is not empty. So this is none of them. And since X is infinite, so this is infinite. This is none of them. So this is not. Okay. Got it? That means it's not closed. So that its closure will be what? That has to be whole X because only X is left out. Right? Got it? Okay. The closure will be a smallest closed set containing that. Here the smallest closed set is X. Because only X is left out. That means X belongs to U bar. Okay? Got it? But look, what will be the sequence? If you have a sequential characterization, if Xn, suppose you sequence in U, then Xn goes to X, but that is not possible because, listen, look, I have already seen it has to be eventually constant. That means Xn will have to be equal to X. Okay, eventually. Right? That means particular X will have to belong to U, but X doesn't belong to U. Okay, so that sequential characterization of closure point is not available in YAN. Did you understand? Read that. Simple thing. But you need, what are the convergence? Convergence sequences are eventually constant. And because of that, sequential characterization of closure point. So sequential characterization of a closure point, a general topological space, is not valid in YAN. So you'll have to be careful. Later on, I will tell you that, if not this semester, next semester, you will understand better that why this is not possible. This is related to cardinality problem. Okay. So that this remark I got 131. Okay. Right. And the thing is, and then 132 house drop I have taught. Here, look, here house drop. Okay. I proved that every convergent sequence has a unique limit in a metric space. But basically, I used the concept that any two distinct points can be separated by disjoint neighborhoods. Same thing if you have house drop, then you can see that result. If let Xt be a house drop space and Xn be a sequence, if Xn goes to X, Xn goes to Y, then X equal to Y. That you need house drop, this result. Same proof will work. Okay. That means here basically you get two neighborhoods. There exists, not all, to V open in X such that, and now look, Xn goes to X, that means U will contain eventually all Xn. Similarly, Xn goes to Y, that means eventually V will contain all Xn. but that is not possible because of that. Okay, right? So that in a Hausdorff space, limit of a convergent sequence is unique. But if it is not Hausdorff, it need not be unique. Okay, it need not be unique. Okay, now look. So that convergence, I have done it here. Let me continuity and not. Now look how I will define continuity. That should be natural thing. That now again I'll have to go back to metric space, see how I define continuity at a point. Metric space, if we have a function between two metric spaces, okay, and x belongs to x, so just see that I got f is continuous at x if given epsilon greater than 0, there exists delta greater than 0, such that I'm doing in, you can take epsilon delta definition right, but that actually means such that f b d x delta, this is a neighborhood of x, small x here, contained in b rho fx epsilon. That's why I told you that you should have it. Okay. That means given any neighborhood, it means given any neighborhood of fx, you get a neighborhood of x such that its image of the neighborhood of x is contained in this. Look, if I talk in terms of neighborhood, I can do that also. I said that f is continuous at x, it is equivalent to this. Given any open set, v containing. So here this is equivalent to that. Given any open set, can easily prove that V containing, sorry, instead V, this is open set you should mention in Y containing Fx, there exists an open set U in X such that of course X belongs to U and if U contained in V. This you can prove. This is equivalent to this. Okay, right. Look here, I do not have any concept of D on that, so I can use this for general topological system. Exactly, we use that F is continuous in top. So only thing here to the topology will have to be replaced. So that means if you have this, let usually define this x tau y sigma. This is a topological space. Let F be a map between two topological spaces. Here topology you have it, and x belongs to x. Then F is called continuous at x. If I don't have the concept of distance, so I'll have to do everything in neighborhood. If given any neighborhood v of fx in y sigma, this topological space. Given any means given a neighborhood. There exists a neighborhood. You should write a in English because if you take it, it would sound like for any neighborhood, the same neighborhood is working. That's not given a neighborhood. This neighborhood will depend on this neighborhood. Given that there exists a neighborhood u of x in x tau such that this is the definition. Okay. whatever we got for matrix was from there we were picking up the idea. Only thing how to get rid of the distance. Okay, so that is continuous. It is at a point. And if like before, if it is continuous at all x, if f is continuous at each point of big X, then f is called continuous on X, or simply say that, or simply f is continuous. When you just say f is continuous, that means you're assuming global continuity. That means f is continuous at each point. Okay, right. Now you look again, two examples. Suppose you have this, like when you take real value function. Here it's we write this. It means here it is giving this metric, giving you the metric topology. So suppose tau is trivial. So which functions will be continuous? Which functions? Are continuous. बताओ. X has more than one point. What we assume. Well, look, suppose there is more than one point. So you have at least 2 points x, y. Okay. Now look, I am saying any 2 points, actually look, I am saying if it is continuous, it has to be constant. Constant function is expected to be continuous. But here I am saying only constant functions will be continuous. Look, how will you prove it? Okay, take any 2 points here. If possible, suppose fx not equal to fy. Okay. If fx is equal to not equal to fy, then suppose 2f delta you take this. Okay. Now fx minus delta, fx plus delta is a neighborhood of fx. Okay. It doesn't contain fy because I have taken 2 delta. So by this there exists a neighborhood of small x which will be contained, but only neighborhood here will be x, because here trivial topology you have only these 2 space. Okay, that means only neighborhood will be fx equal to this, right? But if you have this, then fy will be also here. That means distance between fy and fx will be less than 2 delta, but it equal to I have taken 2 delta. So contradiction. That means f has to be constant. Only constant functions. Got it? Nothing else. Whereas, suppose you take, that I am saying situation, I already told you that topology should be not too big, not too large. Okay, so that you see, now if you take this thing, suppose this is discrete topology. Discrete topology. Now look, any function you take, well, you take any neighborhood. Now look, given x, x itself is a neighborhood of x because x is open. So if you take any neighborhood of this, then I will take this. This is the neighborhood. I will take this equal to u. This is contained in this. So that here any function is continuous is continuous. At each point is continuous. So previously you got only constant functions are continuous, which is expected it should be. And here you are getting any function continuous. That means here you are not being able to, won't be able to differentiate, make distinction between nice function and not so nice function. So that means again here is an example that this is the largest topology, that was the smallest topology. They are not really good enough. Okay, so that topology should not be too big, too small. Okay, so that I have given example 1, 2. Make sure. I hope Bhavna has got well on that. Bhavna, you was not well on page 64. You must do that. I have put a star of A, B. This problems. ये 9 प्रॉब्लम क्या है, पेज 64 में देखना पड़ेगा. That the last result I will do that 9. Here I have given. Make sure that all these problems you do 9 star. Okay. Well, I will do something more general. That is actually this result that I have given that. Okay, I have done it more generally. 9. Okay. So let me just, this is the last result, let me do it. Then I will meet you on Monday. Okay, so that look, this result is saying result in page 133. Here you have two functions between two topological spaces. Here, of course, you have good applications in real analysis, in R, in metric space. You have, and here you will see that what is it. You are assuming sigma is Hausdorff. That means any 2 points Y can be separated by disjoint neighborhoods. Suppose you have two functions, okay, and two continuous functions. Two continuous functions. The A is the set. This. Look, this set is well defined. If they are not equal at any point, then A is empty set. Okay. Then I am saying claiming let equal A is closed. Then A is closed. Show. It's a good result, particularly in algebraic topology. It has good applications. A is closed in X star. Okay. Well, if A is closed in X star, right now I have not given you much of the tools to you for topology on that. A is closed, that means I need to show that X minus A is open. And I have given that, I didn't prove it. X minus A open if and only if each point is in interior point. That means to take this, I need to show if X belongs to X minus A, then there exists open set U in X tau such that I am showing each point is an interior point. This I need to show. In fact, when you are asked to prove something, first you should simplify what actually you need to show. Okay, sometimes it's not very direct that. Look, I have asked you to show it is closed. Then I realize I'll have to show this is open. But in order to show it is open, I'll have to show this. Okay, so you got this. Now look, how you do that naturally. X belongs to X minus 3. Look, where I will use the fact that Y sigma is Hausdorff. If Y sigma is not Hausdorff, result will not be true. Look, X belongs to X minus A by the definition of A implies Fx not equal to Gx, because A is those points where they are equal. But it is in Y. They are in Y sigma. Y sigma is Hausdorff. Okay, so there exist open sets V1, V2. There exist scenes, right? Y sigma is Hausdorff. I'm giving a meaning application also. Where do you need really Hausdorff? There exist open sets V1 and V2 in Y, that means in Y sigma, such that Fx belongs to V1 and Gx belongs to V2, okay, and V1 intersection V2 is, I'm just using the definition of Hausdorffness of Y, okay, right. Now, look, I have given you the function fg continuous. So f is continuous at x. So that because of this, you will get, since f is continuous at x, there exists open set u1 in x tau neighborhood such that I've taken the notation u1 such that x belongs to u1 and if u1 is contained in u1. Now, similarly, here you will get G is continuous. There exists open set u2 in x tau such that x belongs to u2 and G contained in u2. Okay, right. Got it. Now, my claim is that sorry, x belongs to, of course, u1 intersection u2. Look, x belongs to u1, x belongs to u2. So this is trivial, but I will prove this. Okay. That is immediate. You can see that. Because reason is they are disjoint. You will be using this fact. Because if this is not true, they won't be disjoint. Okay. Look, that exactly I proved. Gx prime belongs to Gu2 contained in V2. Fx prime belongs to Fu1 contained in V1. But V1, V2 are empty, so that Gx prime not equal to Fx prime. That is, x prime doesn't belong to A. So we claim. Fine. So this use the fact. For this you need this fact. Okay. Look, actual the Hausdorff you are using here, because the Hausdorff, because of that you are getting, but here you need this thing. Okay. So that when you read a proof, you should be careful where actually you need to use it. Because if you want to go for higher study like research, you should need to understand the techniques. Where you are using what? Where you are using what? Okay. Like, so this is an immediate corollary of that. I said it is closed on that. Okay. So that, like here in that you can do with sequence and that, but suppose you have two functions from R, immediate corollary here to this, and suppose fx equal to gx for all x belongs to q, rationals, suppose, hypothesis. Then f equal to g, that means fx equal to gx for all x belongs to R. Well, look, if you have this, previously I am having A, if you have A equal to this, look, x belongs to R, fx equal to gx. Look, here I am saying on rationals they are equal. It doesn't, I am not saying that outside rationals they are not equal. So that from this it follows A subset of Q. ठीक है? but this implies A bar contained in Q bar. ठीक है? Okay. But Q bar, sorry, I have written wrong way. So I was not getting. Since Q contained in A is all those points where two functions are equal, and I know on Q they are equal, so Q is contained in A. So R is Q bar contained in A bar. But A is closed, that I have proved. So it is A. That means, but everything inside R, I'm working. So A equal to R. Got it? This is the thing in BSc you did, I think, but using the sequential characterization of closure points. Here it is available. Because here they are proof you did take X belongs to R. So there exists a sequence Xn in Q such that Xn goes to X. Okay, in R. Now, since f is continuous, fxn goes to fx. Since g is continuous, gxn goes to gx. But look, xn is coming from q, but they are equal. That means they are the same sequence. So every convergent sequence has a unique limit, but they are same sequence. So fx has to be equal to gx. But x was an arbitrary point in the real life. So f and g are same on R. Okay, right? So these I have said that. Okay, I will see you on Monday. I think I have taught you a lot of that. I think, but you should read that. I will prove that the theorem 3.3 and that many things I talked about and that. So I will meet you on Monday. Anyway, first thing, some of you are asking on that. I don't know whether in the net you will get it. That this is the book, you may enjoy reading it. It is not a big book, a course in what I am teaching you in the topology, that is point set topology, because I am taking points and set. Point set topology, J.B. Conway, actually John B. He is a well-known function analyst, but let me tell you, this book I don't know whether you'll get it. It's a short book. Actually, he's a function analyst. This is actually he's a more especially operator theorist. Okay, he has several books, good books. In fact, next semester he will be doing complex analysis, but I don't know whether he will be using this book. He has a very well-known complex analysis book. It is a bit theoretical, but if you want to learn complex analysis, then you should read his book, Complex. This is Indian edition is available. This Indian edition is available, but this book I am not very sure that Indian edition, but you can try in the net and that. This is a very, it's not a big book. I think I can tell you the page in how many pages it has. It is less than 150 pages. Total it is 142 pages. But it's a very good book because Conway is a very good writer. He's still alive. Okay. So see you on Monday. ठीक है? Okay. Bye.